So there's a word that gets thrown out there a lot, and even I'm guilty of doing this, is isomer. And so an isomer is something that has the same chemical formula, but their atoms are arranged differently. Now, isomer is just kind of this big, broad statement that basically anything with the formula C6H12, any of them are isomers, but within the isomer definition, we have more specific definitions. So the first one we're going to talk about is the constitutional isomer. So I've intentionally done the C6H12. Now, C6H12 can be drawn a few ways. Basically, if we had a saturated alkene, meaning the carbons had as many hydrogens as they had, we would have C6H14. And the rule for saturated alkenes is twice the number of carbons plus 2. So if we have something less than that, it implies that we have carbons bound to carbons somewhere along the compound. And there's two ways to do this. One is to form cyclohexene. The other is to take linear hexene, 2, 3, 4, 5, 6, and put a double bond in there somewhere. So the differences between these two, they are isomers, but these are considered constitutional isomers. And so a constitutional isomer are when we have two molecules with the same chemical formulas, but they are actually varied by bonding itself. So in this case, we have no double bonds. In this case, we do. We have a ring, we don't have a ring here. So there's really no way to get these two compounds to look like each other. Another type of isomer, so here we've got constitutional, is we can have conformational. Board space is a little limited in this video. So to talk about our conformational isomer, let's get rid of the cyclohexene. If we look at this compound and let's say we do the Newman projection along there. Looking down that bond, we'd see something that looks like this. CH3. A conformational isomer, so not constitutional, conformational, is one where we change the compound by rotating it. So we rotate along a carbon-carbon single bond. So if we were to rotate that carbon around and produce something that looks like this, it's Newman projection. Looks like this. So for a conformational isomer, we have to have CC bond rotation. So this can only happen around carbon-carbon single bonds, no double bonds, no triple bonds. And basically we can only have a single bond. So conformational isomers are actually isomers that they are different spatially, but they're easily interchanged, particularly underneath room temperature conditions. Now, there are also what are called stereoisomers. And stereoisomers are a bit more complicated. So stereoisomers have the same connectivity, meaning that if we were to write out how these atoms were connected, we wouldn't be able to tell the difference. They do have a different spatial arrangement though, and there's two ways we can get these spatial arrangements. The easiest one in this figure here is our double bonds. We don't get rotation along a double bond, and because of this, we can't convert, let's say, give me just a minute. This to this. So this is the cis isomer, this is the trans isomer. Because we don't get rotation along the double bonds, these isomers cannot be interconverted. And so we would consider them stereoisomers, and this is where we see easy cis-trans notations for these double bonds. That's why they come about. They are connected in the same way, but there is a different spatial arrangement. The second way we can get stereoisomers is with chirality. So let's abandon this C6H12 and let's go to C11. Br. And we'll draw them the same way. With C11Br, we'll have, let's say we put a bromine on the third carbon. Well, it matters whether or not the bromine in this drawing is pointed out or pointing in because These are mirror images of each other. They can't be superimposed. There's no way to rotate them. So this is where we're going to get the RS notation. So this is the second way we can think about stereoisomers, is if we have some degree of chirality in the molecule. So big things here. When we talk about isomers, big blanket term isomers refers to a lot of different variations, but they're all compounds with the exact same chemical formulas. When we talk about constitutional isomers, we're talking about compounds with the same chemical formulas, but they are bonded in different ways. Conformational isomers are ones where the atoms are arranged differently in space, but we can interconvert them thanks to rotations along, particularly around carbon-carbon single bonds, because we do have that rotation. Stereoisomers are ones where we have the same atoms, so same bonding, but they're arranged differently in space and they are not accessible to each other, meaning that we can't rotate along a bond to get one isomer to look like the other. And two examples of this, cis-trans with double bonds, because they can be opposite, same sides of the double bond or opposite sides, or particularly when we get chirality, this is when we'll get the stereoisomers.